Find non-trivial solutions for x, y, and z. So we have a bunch of equations, basically three equations in three variables. Lambda is some constant, but that's also unknown. Okay, and if you don't know about what trivial, non-trivial means, basically trivial means the simplest solution x, y, z being equal to 0, 0, 0. That's definitely a solution over here because that satisfies all three equations, right? But we want like non-trivial solutions. That means non-zero xyz, non-zero xyz, right? We want non-zero xyz. Okay. So yeah, first of all, let me write it in a matrix form so that it will be easier to like analyze or visualize or look, whatever. I guess you guys know how to write in matrix form, right? Okay. Now, look, let's say if it was in the case of numbers, then for product of two to be 0, definitely one of them has to be 0, right? Over here, definitely this is not 0 matrix, so this has to be 0 to for being 0, right? So yeah, that's definitely a solution. Yeah, but in matrix, there are also cases even when both the matrices are non-zero, their product can be 0, right? Even when the both matrices are non-zero, their product can be 0. That happens in matrix. So that gives us the like some hope that there does exist some non-zero xyz for which the product will be 0, and we want to find them. We want to find the non-zero xyz, right? Now like there's a property that forces multiplication to give 0. The determinant of this matrix needs to be 0. We will also prove that or verify that. We also give some idea why determinant of this matrix needs to be 0, or this 3 by 3 matrix, its determinant needs to be 0. We will verify that in a moment. And if we set the determinant to be 0, we get some values of lambda. For which determinant is 0, and for those values of lambda there will also be some xyz, like non-zero xyz, which give us non-zero solutions, right? So our flow is basically to first find the lambdas and then to solve for the xyz's. Okay, so that's our flow. But first of all, let's see why does this determinant needs to be 0, right? Okay, so first of all, let us believe that there are some non-zero xyz for which there are solutions, right? So let us believe that there are some non-zero xyz, and let me assume that there are some, like, I mean, this is just like a fact, like there are non-zero xyz. That's just some sort of fact for now, and let us assume that this has non-zero determinant. Even when like this is non-zero, like there is also this also has non-zero determinant, and still the product is 0. So let's assume the non-zero determinant, right? And if we assume that, what we get is this xyz, this non-zero xyz this is non-zero xyz, right? And this can now be written as lambda 1 root 2 1 lambda root 2 root 2 root 2 lambda minus 2 inverse times 0 vector, right? So I can take the inverse because I have assumed that the determinant is not 0, and this is a vector with non-zero numbers, right? Now this is the vector with non-zero numbers, and now if I multiply its inverse with 0 vector, definitely we will get 0, right? So what we got is this non-zero vector is equals to 0 vector. That's a contradiction, and that contradiction occurred because the assumption was false. So what is our assumption? Our assumption was that the determinant of this matrix is not 0, and still a non-zero determinant matrix times this non-zero vector is 0. So this assumption was false. So that means the determinant of this matrix like should be 0. Like there's no possibility that without determinant being 0, like these two will be equal, right? Because we saw that if determinant is not 0, then we get a contradiction that non-zero vector is equal to 0 vector. So that's why that's a false assumption, and determinant needs to be 0, then we cannot take inverse. Then this false assumption can, like this false argument, we won't have their contradiction. So yeah. So did that convince you? If that did not, let me try another argument as well. I think that should actually, but still, yeah, I have another argument too. So yeah, because right now, even though we did like so that like there's no possibility of determinant being like non-zero, we still did not like see why determinant should be 0, right? Yeah, though the only possibility left after like being after not being non-zero is the only possibility is being 0, right? That's obvious, but still we haven't why we haven't got the visualization that why it needs to be 0, why it's the determinant needs to be 0, right? Even though that's the only possible case left now, but again, why that should be the case? So you can see it this way now. Okay, I can write this matrix multiplication as x times lambda 1 root 2 plus y times 1 lambda root 2 plus z times root 2 lambda minus 2 is equals to 0. I can write the matrix multiplication like this, right? Because the matrix multiplication happens like this. So basically lambda, if you just see the first row, if you just add these vectors, the first row will be lambda x plus 1y plus root 2z, root 2z, and if you just add these vectors like 1x plus y lambda plus root 2z, so yeah, that's what the matrix multiplication will eventually be, right? Okay. Now if I write it like this, now notice that like this is our, let's say, b1 vector, this is our b2 vector, and this is our b3 vector. Now suppose that if b1, b2, b3, if b1, b2, b3 were linearly independent, then like no vector can be written in terms of other vectors, right? We cannot have any vector be written in terms of other vector, right? So what that means is what that means is they cannot have a relation, like they cannot have a relation with like this x, y, z being positive numbers. So that means for linearly independent vectors, the only solution for this equation would be x is equals to 0, y is equals to 0, z is equals to 0, right? But that's not what we wanted. Right? We are non-zero solutions. So for that, this b1, b2, b3 vector need to be linearly dependent, right? So yeah, now if they are linearly dependent, we know that for linearly dependent vectors, like their determinant will be 0, right? So yeah, for linearly dependent vector, now we know that their determinant needs to be 0, and again, so that will be 0. Now again, if you ask me why the determinant should be 0 for linearly dependent vectors, again, this comes from the argument that determinant gives the n-dimensional volume of n-dimensional like parallelepiped, right? And if they are linearly dependent, like the dimension will be less than, like, okay, over here we are in 3 dimension, but if they are linearly dependent, the span of these 3 column vectors will be less than the dimension, due to which volume will become 0. So there are such things, but again, if you just know that for linearly dependent determinant is 0, that I think that's enough to confirm you. So now we finally believe that for this thing to be equal to 0, with x, y, z being like non-zero, the determinant of the first this matrix should be 0, right? Okay, so now I think you are like, you fully agree with me. Now there are no chances that you disagree. Okay, so now we say that since x, y, z is non-zero vector, determinant of lambda root 2 1 lambda root 2 root 2 lambda minus 2, its determinant should be 0, right? Now if you solve this equation, we will get the possible values of lambda, for which this cannot be determinant 0, right? And for only those matrices, this product can be 0. So yeah, I guess you get the idea of what we are doing now. So lambda is square minus 2 lambda minus 2 minus 1 times lambda minus 2 plus root 2 times 2, okay, root 2 times root 2 minus root 2 lambda is equals to 0. Lambda cube minus 2 lambda square minus 2 lambda minus lambda plus 4 plus 2 minus 2 lambda is equals to 0. This is lambda cube minus 2 lambda square minus 4, 5, 6, and sorry, minus 5. Is it? Minus 5 lambda plus 6 is equals to 0. Now notice that if, let's say, this is the function of lambda, then notice that f of 1 is just 1 minus 2 minus 5 plus 6, which is 7 minus 7, which is 0, right? So if f of 1 is 0, we know that from factor theorem, lambda minus 1 should be a factor, right? Okay, so if lambda minus 1 is a factor, now we want to find what all the factors are. So yeah, I just need to divide this expression by lambda minus 1, right, and get the other factor. I can do the long division, but I think the synthetic division will be more helpful because that's short, right? You can definitely try long division, but let's go with synthetic division. 1, and the coefficients are 1, minus 2, minus 5, 6. This 1 comes as it is. 1 times 1 is 1. Negative 2 times plus 1 is negative 1. Negative 1. I guess you know the drill, right? First of all, what to do is, first of all, write 1 as it is. Now multiply these two. 1 times 1, right over here. Now add these two. Minus 1. Again, multiply these two and right over here. That's negative 1. Now add these two. It becomes negative 6. Now multiply these two and right over here. That's negative 6. Now add these two. It becomes 0. Right? And yeah, if it becomes 0, we know that like the division happens exactly. Like, I mean, there's no remainder in the division. So yeah, now this is our quotient, and this is our remainder, and this is our quotient. I don't know how we say pronounce this. Like, it's called quotient, I guess. I don't know. I'm not sure about that. But I guess it doesn't matter. Quotient. I don't know, something like that. Lambda minus 1, lambda square minus lambda minus 6, right? Now this is like a 2-degree expression. We can easily factorize this, and note that this is equal to 0. So this should be equal to 0. And lambda minus 1, I can factorize this as lambda square minus 3 lambda plus 2 lambda minus 6 is equals to 0. And lambda minus 1, this will just be lambda minus 3 lambda plus 2, right? Okay, yeah, lambda plus 1 is equals to 0. So that means the possible values of lambda is 1, 3, and negative 2. So these are the possible values of lambda for which the determinant will be 0, right? So that means for determinant is 0, it's possible that the product of these two matrices can be 0 even though this one is non-zero, right? So now what we need to do is, for these values of lambda, we need to find the values of x, y, z. For these values of lambda, we need to find those non-zero solutions, because essentially our aim was to find those non-trivial, non-zero solutions, right? And we knew that for only these lambdas, the non-zero solutions are possible, and now we will find out. And you might have noticed that this process is almost similar to finding the eigenvalues and eigenvectors. You can just see them as eigenvalues. Now we are trying to find these eigenvectors over here, and also in the eigenvalues, eigenvector also, it was the similar idea that determinant needs to be 0. Yeah, it's almost the same actually. So now for each of these lambda, let's try to find x, y, z. In x, y, okay, yeah, we will see later on that there can actually be infinite x, y, z, but yeah, we will try to find the simplest x, y, z by taking the ratios. Okay. So first of all, for lambda is equals to 1. For lambda is equals to 1. So we're going to solve this equation. 1, 1, root 2, 1, 1, root 2, root 2, root 2, 1 minus 2 is just minus 1, times x, y, z is equals to 0, right? Okay. Now we cannot definitely solve this by like taking the inverse, because that's only for non-zero solution. Now, one way you can solve this is either you can use those like substitution, elimination method, right? But yeah, I think the more easier approach would just be to use the augmented matrix approach, where what we just do is like you can just write it like this. So if you see this matrix again in this form, if you see it in this form, you definitely know that like this is just x plus y plus root 2 z is equals to 0. I mean, let me just show you. Like for now, if you just see it in this back in the previous approach, this is just again x plus y plus root 2. Say that they are same equations. Root 2x plus root 2y z is equals to 0, right? Now we'll try to use the approach of augmented matrix, where we solve them by writing in a matrix, and then yeah, the idea is the same. Just the idea is to like use one of the equation to cancel all the equations, and then try to reduce it to the like reduced row echelon form, right? That's the way. This idea is just like elimination method, but yeah, we'll do it systematically using matrices, right? Root 2 minus 1 0. So we'll try to reduce this to the like reduced row echelon form, and because the reason is because if once we reduce the reduced row echelon form, it will be easy to see solutions, right? And for the reduced row echelon form, what we should do is basically we'll try to reduce all of them to 0, right? We just want like one, we just want the leading elements to be 1, and in that column where there is 1, we want to make these rest of them to be 0. Again, let's say if here's 1, we want to make the rest of them to be 0, right? So that's the idea of reduced row echelon form. And sometimes it might happen that the equation might reduce to over here, there might be 1. Again, there can be zeros over here, there can be 1 over here, all of them can be 0. This is still reduced to echelon form because the leading elements are 1, right? And then this rest of them are 0, that doesn't matter. And the last one is completely 0, that doesn't matter. Just the leading element should be 1, and in the column where there's 1, the rest of them should be 0. That's the idea. You can also solve them in any way, it doesn't matter, but yeah, this one like turns out to be pretty helpful. Okay, so now first of all, if I want to make this 0, what I can definitely do is, let's say I can do row 2 as row 2 minus row 1, right? Even though I just want to make the first one element 0 because I want both of them to be 0, turns out that the entire thing goes to 0 in this case. And yeah, it doesn't matter anyway. So entire thing will go to 0, 0, 0, 0, root 2 minus 1, 0. Now again, with the hope that we might get 1 over here, what we can do is we can swap the row 2 and row 3. We can swap like row 2 and row 3. I just want to make sure that 1 is over here, 1 is over here in the middle, right? I don't want, even though it's fine that there is 1 and there's 1 and this is all 0, that's also fine. But you cannot have it like this. You cannot have 1 over here. You cannot have 1 over here, 1 over here, and 1 over here. That's not possible. This 1 should also be in the form of, let's say, a ladder, like where you just go either like to the right or down. You cannot come forward. That's just a notion of reduced row echelon form, and that doesn't really have any like mathematical, but that does make things easy. Okay, so yeah, so we are trying to agree with that. So yeah, let's swap row 2 and row 3. This is 1, 1, row 2, 0. So root 2 minus 1, 0, 0, 0, 0, 0, right? Now again, in the hope that we make this one over here 0, what I can do is, I could have actually made this thing also 0 in the first step itself. I could have introduced both the operations that row 3 is also row 3 minus root 2 row 1. I did not do that. If I had done that, it would have been more shorter, but again, I can still do it. Nothing has like really caused trouble to us till now. Okay, so sorry, no, not row 2, row 3, this row 2. I'm sorry guys, I'm sorry. Okay, so row 2 is okay, so row 2 is row 2 minus root 2 row 1, right? And that gives us 1 1 root 2 0. And if I just do root 2 minus root 2 times 1, that becomes 0. This becomes 0. And minus 1 minus 1 minus 2. So that becomes minus 3, is it? Yeah, minus 3, 0, and then 0, 0, 0, 0. Right? Now again, I want to make the leading element 0 1 over here in the second row. Guys, notice that even though there's no 1 in the middle, that doesn't matter, because since the last row is 0, there's not going to be 1 over here. And so yeah, we just need to go like right and bottom, no matter where the 1 is. It doesn't really matter. Like we just shouldn't go back. That's it. So now I can just say that root 2 is negative 1 by 3 times root 2. So 1 1 root 2 0 0 0 1 0 0 0 0 0. Okay, now we have the matrix in the reduced row echelon form. Oh wait, still we don't have, because for the column where there is 1, this all of these things need to be 0, right? And actually there's benefit of this thing, that the reason we want to do it like that is just because we don't want, like later on, if I turn this into equation, we don't want this equation to depend on this variable. We basically call these variables where there's one pivot variables, and where there is not, we call this free variable, right? We don't want the pivot variable to depend on another pivot variable. We don't want one pivot variable to depend on another pivot variable. So that's why we do it. And because basically there's reason for this. But yeah, I don't think we will need that for now. But yeah, the main thing is we don't want one of this equation involving pivot variable. This is the equation involving pivot variable, right? We don't want it to depend on the another like pivot variable. Over here, this is z, right? Now if I just write as equation, this is just x1 plus x2 plus root 2 x3. Let's say this is x3 is equals to 0, right? We don't want these to depend on each other. We just want pivot variables to depend on free variables. So that's why I basically want to make this pivot variable column like free of other numbers, like except 1, other numbers should just be 0. And I can make that using row 1 should be equals to row 1 minus root 2 times row 2. If I do this, that will go to 0, right? So this will just be 1 minus 0, 1 minus 0, root 2 minus root 2 is just 0, so 0. And 0, 0, 1, 0, 0, 0, 0, 0. Okay, now over here these two are the pivot variables, this x and z, and this one is a free variable, which is y, right? Yeah. This is just for knowledge. We don't really need that pivot variable, free variable. Okay, now let's try to solve. Now let's try to write these equations back. So now the reason of using matrix is now this has simplified a lot, right? So now if we write it back, I will just get x1, sorry, yeah, x1 plus, well, this is basically not x1 x2, this is x plus y, right? So x plus y is 0, and we also get z is equals to 0, right? Okay, now over here notice that like this y was the one which was free, right? So I can just let y be t, and yeah, like these x and like z, these do have values in terms of other variables or other numbers. So over here z just has value of 0, and x can be found in terms of y, and yeah, x is negative t. Definitely it's also the case that you might wanna have x as, let's say, t, and then y you can do it as minus t, and z you can do it as 0, right? You can definitely do that as well. It's not that that's impossible. It's just a convention that we first write it in the row echelon form, and we just consider these variables as pivot variables, others as free. That's the South convention. You can definitely, you could have said that x is the very free variable, y is minus t, z is 0. That's definitely possible. But like we just don't do it that way. It's just that. It's not any rules or like mathematical like properties. It's just our convention, okay? So yeah, if you write in reduced to echelon form, it will be easier to find which one do we want to be pivot, which one do we want to be freely assigned, T, S. So that becomes easier. So yeah, that is it. Now we saw that for this value lambda is equals to 1, our solution is this thing over here, right? And now there's a neater way to write it. Again, there's a neater way to write it, that in this way. So I can write xyz as basically negative t and 0. If I take t common, so this will just be negative 1 1 0, right? So basically what I'm doing is, it's just like taking the ratio of the xyz, right? This is t times negative t times 0, and that gives us the simpler answer, that I can either say it 1 minus 1 0, or also I can say it minus 1 1 0. Both of them are fine, right? So I'm just taking the ratios and like taking this t out, so that we get the, okay, over here it's actually x that has minus t, right? And this is minus 1 1 0. But yeah, all the answer is also fine, because I can definitely multiply ratio by my minus 1, and that's still fine. This is also fine, right? But yeah, so yeah, the idea over here, I just took the t common, and yeah, this is just like finding the ratio. This is the simplest answer, like for this lambda, but there are infinite answer for infinite number of t's. Make sure that you don't have t is equals to 0. Definitely t should not be equals to 0, because that will give us the trivial solution. Yeah, for t not being equals to 0, all of these vectors will be our solution for lambda is equals to 1. But the simplest solution is their ratios, which is just minus 1 1 0 or 1 minus 1 0, either of them. You can definitely write this one, and I think this one is as good as the others, right? Okay, so now let's get to the other case where lambda is equals to 2. For lambda is equals to, let's 3. Now the drill is the same. Now I'll just go a bit fast because the video is getting long, right? Then I can just do the same thing. So if there's 3, if it's 3, now I will just substitute lambda over here in this main equation. Okay, I will substitute over here. I can do it over here as well, but I think this is fine, because because eventually we are seeing it in this form, right? Yeah. So yeah, let me substitute lambda is equals 3 in the main equation. So I get 3x plus y plus root 2z is equals to 0. X plus 3y plus root 2z is equals to 0. Root 2x plus root 2y plus 1 z is equals to 0, right? Okay, so now again let's try to solve it using the augmented matrix form. Yeah, guys, and this augmented matrix form is basically helpful when there are infinite number of solutions, right? Because in that case, the matrix inverse way is not able to find solution, because to use the matrix inverse way, there just needs to be single solution. For multiple solution, this augmented matrix form is pretty helpful. Okay, so this is just 3 1 root 2 1 3 root 2 root 2 root 2 1. Okay, again, let's go with the drill. We just want to make it 1. You can either take 1/3 ratio, or you can also do this thing. You can just interchange the row 2 and row 1. That is the easier way. So yeah, 1 3 root 2. This zeros will always be 0, because we are just adding this 0 times something to another 0, so it will never change actually. And I can just ignore that if I want to, but yeah, I'm just doing it for fun. So root 2 1, right? Okay, now I want to make this to be 0, right? Because I said that I want the pivot variable, this leading variable 1, just to be the only one in this column which is non-zero, right? Others should be 0. Yeah, because I already explained why we want that. So row 2 should be row 2 minus 3 times row 1. Row 3 should be rho 3 minus root 2 times rho 1, right? If I do that, this 2 will be 0. So 1, 3, root 2, 0. And over here, 3 minus 3 is 0. 1 minus 9 is minus 8. Root 2 minus 3 root 2 is minus 2 root 2, 0. Now, root 2 minus root 2 is 0. Root 2 minus 3 root 2 is minus 2 root 2. 1 minus root 2 times root 2 is 1 minus 2, which is minus 1, 0. Okay. So now, I want to make this minus 8, 0, right? Okay, let me do that. I want to make rho 2 to be negative 1 by 8 times rho 2. So if I do that, 1, 3, root 2, 0, 0, 1. Now this will be 2 root 2 by 8. So that means 2 root 2 by 2 root 2 square. So 1 by 2 root 2. And 0 minus 2 root 2 minus 1, 0, 0. Now I want to again make this this pivot variable. Wait, isn't there any laser pencil? No, there is not. Is it? No, it's not. This should be one. Okay, no, there is not. Let's fine. Okay, now I want to make this the only non-zero, right? So yeah, I'll make other 0, and how I can do that is I can just say rho 1 to be rho 1 minus 3 times rho 2, and rho 3 to be rho 3 plus 2 root 2 rho 2, right? Yeah. Now if I do that, this will just be 1, and minus 3, that means 0. And now this one might be a bit tricky to calculate. So root 2 minus 3 by 2 root 2, right? So this is 2 root 2 minus 2 root 2 times root 2 minus 3 by 2 root 2, which is 4 minus 3, 1 by 2 root 2, right? Okay. This is 1 by 2 root 2. So this is 1 by 2 root 2, 0, 0, 1, 1 by 2 root 2, 0. And now again this is minus 2 root 2 plus 2 root 2 is 0. And if I multiply that by 2 root 2, that becomes 1. So minus 1 plus 1 is 0 and 0. I was expecting this entire thing to be 0, right? Because only then we could have the like the infinite solutions or the non-trivial solutions. Okay. But anyway, now we know that these two are basically our like pivot variable. This is our free variable, right? This z is our free variable in this case. So now I can write it as x1 plus 1 by no, not x. Why do x plus 1 by 2 root 2 z is equals to 0, y plus 1 by 2 root 2 z is equals to 0. Okay, now the notion of the pivot free variables tells us that I should be assuming z as the free variable t, and then y would just be minus 1 by 2 root 2 t, and z would just be minus 1 by 2 root 2 t, right? Now I can write xyz as x is, oh wait, this is x, right? This is x. Okay, xyz as minus 1 by 2 root 2 t, y as again minus 1 by 2 root 2 t, and g as just t, right? I can take okay, what do we want to take? I think I will want to take this entire thing common. If I just take, let's say, minus 1 by 2 root 2 t common, I will just get 1 minus 2 root 2, right? Yeah, I think and this one is a good solution. This is just like taking the ratio of x, y, z. If I take their three ratios, this will be the answer, right? So yeah, let us also see if this answer actually makes sense. Over here it was minus 1, 1, 0, right? Let us see. Over here if it's minus 1, 1, 0, this is minus 1 plus 0, which is 0. Minus 1 plus 1, 0, which is 0. Minus root 2 plus root 2, 0, which is 0. Okay, that makes sense. Over here, let's see. 0, 1, 1 minus 2 root 2. 1, 1 minus 2 root 2. 3 plus 1 minus 4. 4 minus 4, 0. Makes sense? 1, 3 minus 4. That makes sense. Root 2 minus 2 root 2. That is 2 root 2 minus 2 root 2. That's 0. Makes sense. Yeah. Okay. So this makes sense. And yeah, that's our simplest x, y, z. Right? 1 is to minus 2 root 2. There are infinite solutions, but yeah, that's our simplest x, y, z in the vector form. Or I'm just writing the ratios. There's a reason for that. Okay. Now, for lambda is equals to negative 2, right? Okay, let's do that. For lambda is equals to negative 2. Now let's see what our equation becomes. Negative 2x plus y plus root 2z. Negative 2x plus y plus root 2z is equals to 0. Now next is x minus 2y plus root 2z is equals to 0. X minus 2y plus root 2z is equals to 0. And next is root 2x plus root 2y minus 4z is equals to 0. Root 2x plus root 2y minus 4z is equals to 0. Root 2x plus root 2y minus 4z is equals to 0. Again, let's do the same thing. Now, I think by now you must have gotten bored. Okay. So, 1 minus 2 root 2z. If this is helpful, please do comment because that gives me motivation. Yes, yeah. I see that some of you do comment, and that gives me a lot of energy, and I do yeah, suggest you to. If you enjoy, if you don't, then there's no pressure. Okay. Again, so we want this first thing to be 1, this over here want it to be 1. So what I can do for that is just interchange row 1 and row 2. So this becomes 1 minus 2 root 2 0, and then minus 2 1 root 2 0, and root 2 minus 4 0. Right? Now what I can do is I can just I want to make these two things 0, right? I mean these two 0, right? So for that what I can do is I can just do some row operations. Row 2 to be equals to row 2 plus 2 times row 1, and row 3 to be equals to row 3 minus row 2 times row 1. Row 2 to be equals to row 2 plus 2 times row 1, row 3 to be equals to row 3 minus 2 times. Okay. So now if I do that, this should just be okay, so this is 1 minus 2 root 2 0 itself. Now that's 0, and 1 minus 4 is minus 3. Root 2 plus 2 root 2 is 3 root 2 0. And again, now root 2 minus root 2 is 0. Root 2 plus 2 root 2 is 3 root 2. Root 2 plus 2 root 2 is 3 root 2. Minus 4 minus 2 is minus 6 times 0. Yeah? That makes sense? Let me see if that makes sense. Yeah, okay, makes sense. Now I want to make this thing 1, right? So row 2 is equals to minus 1 by 3 of row 2, and that makes it 1 minus 2 root 2 0 0 1. Now this is just minus root 2 0 0 3 root 2 minus 6 0. I want to make these two things 0, so that becomes row row 1 to be equals to row 1 plus 2 times row 2, and row 3 to be equals to row 3 minus 3 row 2, right? If I do that, this will now be 1, and minus 2 plus 2 0, minus 2 plus 2 root my root with root 2 minus 2 root 2, that's minus root 2 0, right? and this is again 0 1 minus root 2 0, and now this will just be 0, that's just 0, minus 6 plus 6, that's also 0. So again this, I knew this are going to happen because the because over here these were already our pivot variables, so this had to be our free variable, right? This g had to be our free variable. Okay, so over here we see that x minus root 2 z is equals to 0, y minus root 2 z is equals to 0, and g is free. So let g be t because g is free variable. There's no restriction on g. So y is equals to again the root 2 t. Again, guys, as I told you earlier, like you can definitely, it is definitely the case that you can also say x as t first of all, and then you can say that g is just 1 by root 2 t, and now you can find y as just 1, that just t. That's definitely the case. But we are not doing that because we say we are just making it systematic, right? We are saying that x and y are pivot, the z is free. So yeah, we are doing this. So we are just trying to make it more systematic, and that's definitely the case that you can assume any of them to be t. Okay, and this is more helpful in like in higher dimensions. Okay, so yeah, y is root 2t and x is root 2t. Now if you know this, now I can write x, y, z to be, I'm sorry again, this is x y, z to be root 2t, t, if you take t common, this is just root 2, 1, and this is the simplest ratio between x, y, z. That's root 2, 1. And yeah, there are infinite solutions within this. Over here t should not be equals to 0, because if t is equals to 0, that gives us the trivial solution which we don't want. So yeah, this is the simplest ratio, and let's try if that works. So root 2, 1, right? So minus 2 root 2 plus root 2 plus root 2, that's 0. And what was it? Root 2, 1. Okay, root 2 minus 2 root 2 plus root 2, that's 0. This is 2 plus 2 minus 4, that's 0. Yeah, okay. This also works. So we see that all of these three simplest solutions also work, and yeah, corresponding to each of these three simplest solutions, there are infinite solutions. So yeah, there are three sets of infinite solution for these three lambdas, and for these three lambdas, our determinant is like dependent, right? This is not, this is becomes an independent matrix, and yeah, so we have like non-trivial solutions, and all of the, we have found all of them. So this was it, guys. Hope you enjoyed the video. Thanks for watching. Hope you learned something, and look forward to seeing you in the upcoming videos too.